In this video, we will discuss about process variation and process corner simulation in Cadence. As we know, when we make an IC, it involves a lot of process like oxidation, diffusion, ion implantation. A lot of processes are there. So as a result, we will not get exact result of what we do in the layout or in the circuit. For example, if I make a resistor with polysilicon or with metal, we make the resistor like that in the layout. Suppose I made the resistor like this. So this is the resistive area, this is the contact. So this is what we draw in layout, and we are expecting a resistance value of R. But in reality, when you do the process in the IC, you will not get exactly the same shape. So see, what you will be getting some irregular structure like this. So the resistance value will vary. It will not be a constant fixed value. So with respect to process, the resistance value will vary. We know the resistance R equal to rho into L by area is the equation for resistance. But this length, this area is the thickness into width. So this is the width, this is the length. So thickness will be in the downs. Okay. So the length will vary, area also will vary, and according to the doping and other process, the rho also can vary. So when you assume I made a resistor with 1 kilo ohm in the layout or in the schematic. In the IC, you cannot expect exactly 1 kilo ohm. So there will be variation in the resistor, in the resistance value. So in reality, in silicon, you cannot make exact value for resistor. This is not just for resistor, this is equally applicable to capacitance also. You cannot make exact capacitance value in the silicon. So when I make a resistor of 1 kilo ohm in the schematic, in the silicon I may get 0.7 kilo ohm, 0.8 kilo ohm, 0.9 kilo ohm, 1.1 kilo ohm, 1.2 kilo ohm. This will vary. So I cannot exactly make a resistor in silicon. So how much this variation can go. So the resistance value I am writing as R silicon equal to the resistance you actually designed plus or minus delta R. So when you make a silicon, when you make a resistor in schematic, assume you made a resistance with value R. Its value in the silicon can increase or decrease. I am plotting a graph here. So this is the resistance. Resistance is in the x-axis, and assume I need a resistance value. So this is the resistance value I need. Assume it is 1 kilo ohm. So with respect to process, the resistance can increase or the resistance can decrease. So how much this can increase or decrease? So each manufacturer, that means each foundry, will model their resistance and capacitance, and they will say maximum variation will be up to this much. So that is called process corner. So this is my typical resistance value. So this is the maximum it can go. So this information will be provided by the foundry. They will say that according to their process, if you make a resistance R, the maximum value will be this much percentage. It can be 10% or it can be 20% or even 30. And like that, the minimum value it can go is the another corner, minimum corner. So for a resistor, when you make a resistor with typical value, the actual resistance value in the silicon will be in between any of these points, any of these corners. That means from minimum to maximum. So the real value will be in between any of these. So the corners, so these two extreme value we call as process corners. It doesn't mean that either it will be in typical or in minimum or maximum. It doesn't mean that. It could be anywhere in between minimum and maximum. So some foundry call the process corners minimum corner and the maximum corner. Like UMC and other foundry call like minimum maximum. But some other foundry like AMS, they call it as worst power and worst speed. Assume your resistor, you fix a voltage VDC and you have resistance R. Assume the resistance value decreased, the resistance value is less than the typical value, then the current through this will increase. That means the power will also increase. So that's why minimum resistance means more current, so WP, worst power. And when the resistance is higher than the typical value, then the current through that resistance will be less, and that corner is called WS. So for AMS process and some other process, they specify the corners as WP and WS. So now let us consider the case of a Mosfet. And in the Mosfet, what are the things can vary? First of all, oxide thickness can vary. In the process corner, the oxide thickness can vary. You cannot exactly say this will be my T-ox. Thickness of the oxide can vary from chip to chip. Even within a wafer, the oxide thickness can vary. And the doping concentration and other parameters can vary with respect to process. So as a result, the VT will vary, threshold voltage will vary, and you cannot, even though that there will be a typical value for the threshold voltage, you cannot say that, see, this is my threshold voltage. That there is no absolute value with respect to the process. This VT will vary. We will see all these things in the simulation, and we know the current equation for Mosfet in saturation is mu1 COX W by L into VGS minus VT whole square by 2. In this equation, the VT will depend on the process. So VT will vary with process, and this term also will vary with process. So when you design a circuit, you should make sure that your circuit is tolerant to process variation. Because of this variation in VT and other parameters, the current through the Mosfet will vary according to the process. So now I am plotting for the Mosfet. If I plot the Mosfet current and resistance, current and speed, so this is my Mosfet current I, and I can write the speed also. If the process variation of VT and other is in such a way that the current is increasing. For example, if Vt is decreasing than the typical value, then the current will increase. So I am making this as my typical point. If Vt is increased and mu COX into W by L term will increase, in that case, the current through the MOSFET will be higher than the typical value. So it can go up to some value. So the process, the foundry will specify this is the maximum it can go. Okay, so this is what high speed. This is a fast corner or high current corner. Like that, Vt can increase and the mu COX W by L term can decrease also. In that case, that means if all the process corner is occurring in, all the process variation is occurring in such a way that the speed of the MOSFET is decreasing or the current through the MOSFET is decreasing, in that case it can go up to some minimum value. That is the other corner. This is the slow corner. So every MOSFET will be in between this slow corner and this fast corner. So you cannot exactly say that your MOSFET will be in typical always. So when you design a circuit which is involving the MOSFET on all this, you should ensure that your circuit is robust to process variation. So its threshold voltage can vary, and it is the current through the MOSFET can vary, and the speed of the MOSFET can also vary. So your MOSFET will be in between here any of this value. So you have in CMOS process you have NMOS and PMOS. So the process variation can be independent. For example, there could be one you made a chip and it could be slow NMOS and fast PMOS, or it could be fast PMOS and slow NMOS, or it can be fast PMOS, fast NMOS, or slow PMOS, slow NMOS. So there are 4 combinations in this 2 MOSFET itself. So the foundry such as UMC and other, they will specify these corners as SF. That means slow NMOS, fast PMOS, and FS, that means fast NMOS, slow PMOS. This is NMOS, and FF means both NMOS and CMOS are in the fast corner, this corner, and this slow NMOS and slow PMOS both are in the slow corner. That we can draw in the graph. Here I am plotting the current and speed of NMOS in the x-axis, in the y-axis current and speed of PMOS. So first I am marking the NMOS corners. So I am considering this as the NMOS, slow NMOS. That means when NMOS corner is here, this is a slow NMOS, and when NMOS corner is fast, so I am marking here is the fast N, and for the PMOS, this is the PMOS axis. So the fast PMOS will happen at here, and the slow P will appear here. So when I plot the graph for NMOS, I mark the slow NMOS here and fast NMOS here. Like that I can mark the slow NMOS here also, because in the y-axis it is the same for now I am plotting only the NMOS corner. So here slow N means here also it is will be slow, and here it will be fast. So these two are same corner for the NMOS, and these two are same fast corner for the NMOS, and these two are the same slow corner for the NMOS. So now we have 4 points. So this corner, so this corner is slow for NMOS and fast for PMOS. This is slow NMOS and slow PMOS. This is fast NMOS and fast PMOS. So this is fast NMOS but slow PMOS. So you can make your typical corner here. This is the typical. So when you make a CMOS circuit with NMOS and PMOS, so you can have a combination with fast NMOS and fast and slow NMOS PMOSs. So your device will be anywhere in between these two. So these are the 4 process corner. So when you make a circuit and your circuit is working only in the typical corner, then the yield of your circuit will be very less. Suppose you made 100 chip. So out of that you cannot expect all the chip is in the typical corner. It can be slow P or slow N, and anything will happen. So if your circuit is robust to process corner variation, that means it will work in all these 2 corners or in between all these 4 corners. Then your yield will be high. That means if you made 100 chip, out of 100 you can use 90 or 99 you can use. So I already told you that some foundry will call SF, FS, FF and SS, but some other will call worst power, that means fast P and fast N, worst speed, worst speed means both are slow N and P, and other. So what the name we call for the process corner will vary with foundry to foundry, but the basic idea is the same for all. So we discussed the process corner variation in resistor and Mosfet, but this is applicable to capacitance and bipolar transistors, and the foundry which is making the IC, they will specify all these models. They will provide you a typical model. They will provide the fast corner model and they will provide the slow corner model also. And you can make all this combination to check your circuit whether it is robust to process corner variation or not. So now we will go to the Cadence and see the process corner variation in the simulator. Let's go to Cadence now.
Hi, in the last session we discussed about the process corners and the process variations, and we said all the manufacturer or all the foundry will give you the information about how much it will deviate from the schematic to silicon. When you make a device, make a device in schematic, it will not be exactly the same when we make on silicon. There will be variation due to process. So how much it will vary is given by the process corner. So in this video here I will demonstrate the process corner process variation of the devices. To demonstrate the process variation, I start with the resistor. So initially I will do a simulation with ideal resistor, that is a resistor from the analog library. It will not change with the process or anything. It is an ideal resistor. So initially from the analog library, I select the analog library. From the analog, I want a resistor. I selected the resistor symbol, close this, and okay, the resistor value is 1 kilo ohm by default, and I place the resistor. I need a voltage source now. I'm using a VDC of 3 volt. Okay, I need a ground. Press escape, just wire them together. Save the schematic, and I am just running a DC simulation to see how much current is flowing through that resistor because of that voltage source. I selected DC, save DC operating point. I'm not sweeping anything. Okay, save. OK, run the simulation. And to see the output, we have to annotate the DC operating point. So we got the voltage across this resistor is 3, and the current through it is 3 milliampere, and the power is 9 milliwatt. So this is an ideal resistor. It will not vary with the temperature or process. Now I am inserting a real resistor. I am inserting a poly resistor. I am inserting a resistor made of poly. So I want exactly 1 kilo ohm, so that it match with the ideal resistor. So this is a resistor with polysilicon with a 1 kilo ohm. So by the value, this resistor value is 1000 ohms, that is 1 kilo ohm. Okay, and this resistor value also 1 kilo ohm. So now you run the simulation. Let's see how much current is flowing through each resistor. Go to result, annotate DC operating point. See here, this is the ideal resistor. So we got 3 volt by 3 volt by 1 kilo ohm, 3 milliampere. Here it is a real resistor, so we didn't get exact 1 kilo ohm, but it is very near to that. So we get current I equal to 2.94 milliampere. It is near to 3 milliampere. This is not because of process corner. This is in the typical corner itself. To see which using which model file we are simulating, you can go to setup and model library. See, here you can see this CMOS library is CMOS typical model. Resistance library is model file is resistance typical model. Click on that resistance. You can see the other model files. This is the typical model, and this is resistor for worst power. Worst power means minimum corner, and resistors WS for resistor WS for worst speed. And this is for Monte Carlo simulation, and we are not explaining Monte Carlo simulation here. So in this simulation we did the simulation with typical corner itself, and we got these values. So before doing the simulation with any other corner, just note down these values. I am adding a note here. With ideal resistor we got 3 milliampere. So I am placing it here, and with real resistor, or we can say poly resistor, and in typical model I am writing TM, we got 2.943 milliampere. Now I am not changing the value of the resistor. The value of the resistor is 1000 ohm itself, but in the next simulation what I am going to change is the model file. So go to setup and the model library. In the model file we are using the typical corner. Now I am moving to worst power corner. Worst power corner means the resistance value will decrease, and current through that resistor will increase. So that's why it is called as worst power. So worst power corner will happen when due to the process variation, if the effective resistance of the effective value of the resistance is decreasing in the process, and then the resistor WP, that means worst power corner, will happen. So this is the maximum deviation from the typical value. This is the maximum decrement that we can expect from the typical value. So I changed that. I changed the model file and running the simulation again. You can see the current now increased to 3.90 milliampere. See, the voltage across the resistor was the same. The voltage across the resistor is same, and the resistance value is same, 1000 ohm only, but the current through the device increased. What does that mean? Current through the device increased means the resistance value decreased. So initially in the typical model it was 1000. In the typical model, when we say 1000 ohms, it was 1000 ohm itself. But now in the WP corner, that is minimum resistance is in the minimum corner now. So in that case the resistance value has decreased. Okay, we can edit this like okay, we got 1000 ohms in the typical model. But in the worst power corner, that means in the resistor minimum corner, we got the current 3.90 milliampere. So let's calculate what is the resistance that is coming on that corner. So you can calculate the you can find the resistance value by voltage divided by current. So 3 divided by 3.9, I am doing it on my calculator. The value is 0.769. That means instead of 1000 ohms, now we have only 770 ohms. You got the point. What we targeted is 1000 ohms, but due to the variation in the process, we got, instead of 1000 ohms, we got only 770 ohms. So this is the maximum variation, maximum decrement you can expect from this process, from AMS process. So this is modeled by the manufacturer, so we can record that. So again, poly in the typical model, now poly in the worst power model, we got 3.904 milliampere, and the resistance value we got is approximately 770 ohms. Okay. Now keeping the same value 1000 ohms, we change the model file again. Now we simulate in the worst speed, that means maximum of resistance value. So instead of resistance model WP, we can change this to WS. Okay, now run the simulation, and you see now the current decreased. The current decreased to 2.3 milliampere. That means for a fixed voltage, if current is decreasing, that means the resistance value has increased. So you can find the resistance value by dividing 3 by 2.322. That gives a value of 1.29. So this is the worst speed corner, that means maximum resistance corner. So we can write it that also into our table. We can edit this table now into, this is WS, that means maximum resistance value. Now the current for that WS we got 2.322 milliampere, and the resistance value corresponding, that is 1.29 kilo ohms. That means 1290 ohms. Okay, so in this simulation we simulated a 1 kilo ohm polysilicon resistor in different corners. So in the typical corner, the value is 1000 ohms and the current was 2.94 milliampere when we applied a 3 volt across it. And in the worst power corner, that means resistor minimum corner, the resistance value decreased to 770 ohms and the current increased. We got 3.9 milliampere. In the worst speed corner, that means maximum resistance corner, the current decreased to 2.32 milliampere. That means the actual resistance value, the effective resistance value at this corner is 1290 ohms. So all this variation from 770 ohms to 1290 ohms will happen when you make a resistor of 1 kilo ohm. So when you make a resistor of 1 kilo ohm in the schematic, after the process, when you get the IC on your hand, the resistance value could be anywhere in between 770 ohms to 1290 ohms. So you can see how much variation is happening. So you can calculate the variation by 1000 minus 770, and by doing the calculation you can see the variation. So you have to keep this in mind when you design anything with the resistor, that the resistance value is not a fixed one, it will vary with process. So when you design a circuit, you make sure that that circuit will work irrespective of this variation. So when you design a circuit, it should work, that circuit should do is functionality even if the resistor is 770 ohm or if it is 1290 ohms. So I repeat, when we make a resistor of 1 kilo ohm, this much variation will happen. So this even if we make a higher resistance also, then also correspondingly this much percentage of variation will happen in every design. So this is the process variation of resistor. Now let's check the process variation of MOSFET.